Now that we've looked at the idea of taking derivatives, let's do what probably going to come natural, taking integrals. The definite integral of a continuous vector function r of t can be defined much as we do for real valued functions. Just as we take derivatives of each component of a vector function, we're going to do the exact same thing to integrate. We'll simply take the integral of each component. So let's jump right into an example. So I have this vector function in component form. And what I want to do is I want to find the integral of this. So the integral of r of t dt is equal to the integral of cosine of t I dt plus the integral of sine t j dt plus the integral 2tk dt. Well, the integral of cosine of t is going to be sine t. So this is going to be sine t I plus the integral of sine of t is negative cosine of t j plus the integral here is going to be t squared k. So this integral is equal to, back in component form, sine t negative cosine t squared. That's really, honestly, that's simple. Now, the cool part about this is that we can take the fundamental theorem of calculus can be extended to vector functions as follows. So notice that the way I did this first one was an indefinite integral, and actually this should be plus c, and I'm going to have this this constant here that's kind of floating around. And actually, because of that constant, it's probably not a good idea to write it like this. We really should probably leave it in the basis vector form. So I probably should just leave this as sine of ti, oops, this could be a minus cosine of tj plus t squared k plus c, and c is the constant of integration, but in this case it's the constant of vector integration. Now, as I was saying, the fundamental theorem of calculus can be applied, and you know when we have a definite integral, because this one was indefinite, that c goes away because it cancels itself out. So the integral from a to b of r of t dt is equal to r of t evaluated from a to b. This is using the standard notation that we've used before for antiderivatives. We're talking about definite integrals, where capital R of t is the antiderivative of small r of t, and that's actually equal to, oops, not r of t, I'm sorry, r of b minus r of a. That's exactly what the fundamental theorem of calculus has told us before for real valued functions, and it's the same thing here for vector functions. So take a look at this previous example where r of t is this guy. Then the integral, I'm going to take the integral from, say, 0 to pi over 4 of r of t dt. That's going to be equal to, I'm going to write it in component form, sine t negative cosine of t squared evaluated from 0 to pi over 4. So that's going to give me sine of pi over 4 negative cosine of pi over 4 pi over 4 squared minus sine of 0 negative cosine of 0 and 0 squared. Well, sine of pi over 4 is root 2 over 2. Negative cosine of pi over 4 is negative root 2 over 2. And obviously, pi over 4 squared is pi over 4 squared. Minus sine of 0 is 0. Cosine of 0 is 1. Negative cosine of 0 is going to be negative 1. And, of course, 0. So that's going to end up giving me the vector root 2 over 2. Negative root 2 over 2 minus a minus 1. That's going to give me, well, 2 plus root 2 over 2. And, of course, pi over 4 quantity squared. That's it. That's all there is to it.